My name is Marc Goodfellow. I'm coming here from the University of Exeter. What I'm going to talk to you about is an application to try and understand epilepsy and make clinical predictions in epilepsy using mathematical models and data analysis. So I'm going to talk you through some standard analyses. We're going to ask questions about why these may or may not be used in clinic already, and then talk through to mechanistic models, how we use those to try and understand what's going on in seizures. So we've heard a little bit about epilepsy already, but I mean by definition this is the propensity of the brain, or the brain of somebody with epilepsy, to generate recurrent seizures. So one seizure isn't enough to be diagnosed with epilepsy, rather this has to happen multiple times. And these are quite severe changes in brain dynamics with observables on the EEG. So often in epilepsy, not always, but there isn't such an issue when recording seizures of signal to noise. So these are obvious changes in dynamics that go along with certain signs and symptoms that can be bespoke for different kinds of epilepsies. EEG is going to be a crucial tool here. So different kinds of EEG. We start with the scalp EEG here, for example. This is a much used clinical tool in epilepsy. It's used to make decisions on diagnosis and also to guide treatment. Often the aim is to record abnormal EEG dynamics, for example seizures or interictal activity, so spiking that shouldn't be there in otherwise healthy brain dynamics. But I'm also going to talk just a little bit about alterations to background or resting dynamics as well. So I've been working on this topic, on this broad topic, for a number of years, together with clinical partners and also experimental partners. And these are just a handful of the important questions that I thought I would throw down on this slide. I kind of started here from a dynamical systems perspective on trying to understand why do seizures start and stop. Over my career, I've moved into more applied or clinical questions. For example, how do we make an accurate diagnosis of epilepsy, or how might we use signal analyses and models to try and predict prognoses from treatment. And treatment for epilepsy is varied. Pharmacology is the first line usually, but quite famously it doesn't always work. So around a third of people with epilepsy are refractory to pharmacological treatment. And in that case we need different kinds of intervention, and surgery is quite a common one, for example. The idea is to remove brain tissue that you think is generating seizures. So if you remove that tissue, then therefore seizures cannot be generated anymore. So I'm interested in exploring which signal processing approaches are used in research and as opposed to those that are used in the clinic. So I was talking a little bit yesterday about clinical neurophysiologists, and I think most often it's fair to say that the kinds of analyses that are used in clinic are often qualitative and based on clinician experience rather than being quantitative and based on signal processing's research. And I thought, so obviously we've all been talking about different rhythms in the brain. Here's an expose of some typical rhythms that we can record on EEG or implanted electrode devices, for example. And we can think about simple signal processing technologies such as Fourier transforms, or wavelet transforms, or looking at these in the spectral domain and assessing how much power there is in different frequency bands, for example. And I just pulled up here a recent paper based on a search of quantitative EEG approaches to inform clinical decisions in epilepsy or so. And we can see, for example, that if we compare people without epilepsy to people with epilepsy, there are differences in the resting rhythms. There's, what do we see here? A higher power in delta rhythms, which are these slow, roughly to 4 Hz rhythms, and also a higher power in theta rhythms, for example. There's a plethora of literature on this, and we even saw from Jean-Marc yesterday about differences in sleep rhythms as well that have been observed. And I'll talk a little bit more about that later. These are intrinsic signal properties. It's also interesting to look at how these signals are distributed throughout over different sensors or networks. The buzzword for this is functional connectivity, which means an assessment or a quantification of a statistical association between different channels. So, for example, a particular method of assessing this, the imaginary part of coherency, is shown to be increased when you calculate this within theta bands. This is quite an interesting paper, actually. It's one that I've just came across when I was putting this talk together, because it's actually looking at a more nuanced question, not just are controls different from people with epilepsy, but are people who go on to have epilepsy different or quantifiably different from those who just have a single seizure? And there are some hints here of different brain rhythms in in that case. So, and I was going to ask this question yesterday when Jean-Marc did his talk. This is a huge literature, often studied, and we talked about this a little bit yesterday, often done in small samples from independent groups throughout the world. And we know that these quantitative differences exist, but are they used in clinical practice? And the answer, I think, is resoundingly no. So it's interesting for me to explore, also in the context of this meeting, how we change that, or what needs to be done to change that kind of way of thinking or way of practice. What kind of evidence would be sufficient? So these were some results from background and from simple brain rhythms. We know that brain rhythms in epilepsy are far from simple, though. For example, when we look at seizures or seizure onset patterns, and this graphic isn't so great in its resolution, but we can see different kinds of rhythms that are associated with seizure onset. So I think the onset point is the asterisk here in each case. This is the demarcated seizure onset. And we can see patterns of qualitatively different seizure onsets. And there is an aim to relate these to different underlying pathologies, but that's very difficult. And one of the things that I've been interested in throughout my work is how we might understand these mechanistically, relate these different dynamics that we observe to what is going on actually in the brain during seizure. We therefore would turn to, what would I say, nonlinear time series analysis, so going beyond kind of spectral analyses into ideas from symbolic dynamics or even from nonlinear dynamics. And I would just highlight here one such method which came to my attention over 10 years ago. It's fairly modern actually, which is the horizontal visibility graph. And I've come into using this a little bit more recently. So the idea is that we can turn a time series into a network. I don't know if anybody's familiar with this method, but it's quite interesting. So here are the data, the sequential data points in our time series. And we turn this into a graph where each time point is a node, and we can connect two nodes if there is a clear path between those time points. So this pattern here is concave, so we can draw that line here, whereas T1 and T4 are not connected because there's this intervening higher point in T3. So I thought I'd show you, I thought I'd introduce this because it's going to become important later, but also to highlight an application of this kind of, I guess, more non-linear kind of time series analysis in epilepsy, which was done by a collaborator of mine and friend, Caspar Schindler, and his team in Bern, who are interested in the non-trivial or more nuanced aspects of rhythms that emerge in the epileptic brain. So these are epileptiform rhythms that are often spike-like, for example. And he was interested to quantify this in terms of time irreversibility. And there's a natural or a nice way to do this with horizontal visibility graphs, which is that you make the degree distribution of your graph for the out degree and also for the in degree. So it's a comparison of the graph that you make forward in time and the graph that you make backwards in time. The degree distributions for these are equal if your signal shows a degree of symmetry, so forward-backward symmetry or time reversibility. So here we see the in and out degree distribution from this graph, and you can see that it's roughly the same between the in and the out. Whereas for an epileptiform rhythm, which in this case is sawtooth-like, this is quantifiably irreversible in the sense that the out degree distribution and the in degree distribution from this HPG are different. And this was quantified in this study by the p-value in a Kolmogorov-Smirnov test. So this was shown to be important for epilepsy because actually, if you quantify this time irreversibility, the irreversibility is greatest in the seizure onset zones or in the zones that, if you remove them, can render a patient seizure-free. So there's a relationship between these more complex quantifications of brain signals and the fact that they are able to generate seizures. So the fact that they are part of the epileptogenic zone. Again, so this is 9 years ago. Yeah, maths is right, 9 years ago-ish. And there's some decent evidence there from a small population in a department that is very research focused, maths and physics focused. So Casper, Casper is a neurologist. I think he also did his PhD in physics. He's working with physicists. So this is a team that is ripe to generate these insights, use these different, more nuanced methods. But is this technique now being used in clinical practice? And the answer is no. And this is quite interesting again to me. And I actually questioned Casper about this quite recently. I had an interaction with him about a year ago now, and I asked him this question. So he's worked on quantitative EEG for many, many years. And in your department was the question, which of these approaches are now used? And he had to put his hands up and say, honestly, they're not. So going, I guess on the theme still of non-linear dynamics, this is an approach that we proposed again 9 years ago and followed up a little bit more recently, which is to try and understand the ictogenicity, or if you like, more abstractly, the excitability of networks. So the idea behind this is what Mark Richardson and John Terry coined at the time, brain network ictogenicity, which is given a network structure, so we're entirely thinking about network effects here. Given a network structure, how likely is it that that network can generate seizures? And how we assess this is we bring it to life using a dynamical system. What we use here is the normal form of a SNCC bifurcation. So this is a one-dimensional model that can generate spikes if it passes through a threshold. So it's a very simple neuronal model. That is but one method of modelling state switching dynamics, and I did a little bit of work on the various different dynamical system sort of approaches to this. We focus in on this one for now because we had also found it in a neural mass model, and I'll talk about neural masses in a bit. The idea is that we take a network with a given structure, and we can bring this network to life by putting some spiking dynamics on it. So we can tune a global coupling strength here such that it generates seizure or spiking activity. This is our proxy to seizures. And we quantify this seizure-like activity roughly by the time that it spends spiking as opposed to not spiking. And we can tune it into an operating regime where it has a BNI of 0.5, so it's generating spikes or seizures 50% of the time. What we can then do is start to simulate virtual resections. So this is in an aim to understand why certain networks might be amenable to surgical resection in epilepsy, and whether we can predict who would benefit from surgery, whether we can provide patients with diagnoses for if their resection will work. And more crucially, how to define a priori what the optimal resection should be. So here, carrying on with the nonlinear dynamics theme, we quantified functional connectivity from signals recording during the seizure period, and we did that by a mutual information measure. So from the time series, we go to a functional connectivity network. And these are recordings, I must say, from intracranial EEG. So these are closer to, this is part of the epilepsy surgery workup, where the team is trying to delineate where the epileptogenic zone is. And if you like, this is our network model of the epileptogenic zone, in which we can then remove a node. So we calculate the BNI, we set it into this operating regime. There's a 50% seizure occurrence. We remove a node and ask the question, well, does that reduce the amount of seizures in the dynamics? So we're making a quantification of the causal influence of each node or each set of node on the dynamics. And what we did more recently was start to actually make a principled optimization of which set should be removed. So in a large network, these can get up to, for example, hundreds of sensors. It's intractable to try and elucidate every combination of nodes that can be removed, but we use genetic algorithms here to find the optimal. And here's an example of how this works in people with seizure freedom post-surgery. So this is what the Engel category is. Engel 1 is post-surgery seizure freedom. Engel 4 is no effect of the surgery. We have here in orange the nodes that were removed from the network. And we have in pink or purple the nodes that our genetic algorithm suggests that under the assumptions of the model would be the optimal ones to remove. And in this optimization, obviously, we trade off reduction in BNI with trying to keep the resection size small as well. So this can be a multi-objective optimization. So we do that for good outcome patients and poor outcome patients in a retrospective study. And what we find is that there is a greater degree of overlap in our prediction for which nodes should be removed in the good outcome cases versus the poor outcome cases. So this can begin to be a model-based strategy for trying to optimize somebody's epilepsy surgery. We find that there's quite a good classification based on this. Again, so this is, I can't remember how many subjects we had here, order of 20 to 30, I think. And there are various other groups around the world, obviously trying to use quantitative methods to optimize surgery. And there are various different ROC curves that look something like this. And each center is using some sample of subjects from their previous surgery cases. Is this being used in clinic? No, it's not. But we are actually trying to find ways now to advance this. So, for example, we're hosting a neurosurgery trainee on a fellowship. So we actually have somebody who is training to do neurosurgery coming and working with us and learning these methods. This, I think, should be, or at least up there, in terms of a tangible pathway to getting things like this used in the clinic. We hope. So back to how do we understand altered brain rhythms in epilepsy? And this comes back to the question of why do seizures start and stop? But we'll also see that using models, we can get to the question of, well, which drug should I prescribe? So I'm going to talk you through this a little bit. We've talked a little bit already, and I think one of the big discussions in this group is a question of scales. So how do we understand or model the brain? Which scales should we use? Neural mass models were introduced a little bit in the first talk of the meeting, and this is what I'm basically going to introduce. So, for sure, in epilepsy, we're most often recording macroscopic signals. I mean, there are some methods to record single units. But if we're talking about routine clinical use, we are recording electrographic fields that are generated in large regions of tissues. We're interested in these kinds of dynamics. So we focus here somehow on models of brain tissue. And as we've seen before, these are not just networks of neurons, they are tissue in a milieu of exotic chemicals and cells, and how we abstract from a neural network up to the dynamics or the properties of these tissues is still quite unclear to me. But models for this do exist, and I'm going to talk about, or briefly introduce, the neural mass model. There are different flavors of these, but essentially what we do is we abstract the working or the function of a neuron or a set of neurons into being input to output converters. So a population of neuron takes some activity as input, and its output is then a postsynaptic membrane potential change together with some outgoing firing. And this is how we build up networks. This is a lot of this stemmed from work in the 60s by Walter Freeman, for example, who would isolate the olfactory bulb, fire some inputs into it, and observe on the tissue level, so the region of a demarcated region of the brain, what the rise and fall kinetics of the LFP would be. And we see this simple exponential rise and decay, which can be modelled in a second-order differential equation with time scale and gain parameters. And this forms the foundation of these kinds of neural mass models. So we have some input that forces through a synaptic response. This leads to a change in membrane potential or excitability at the level of the neural mass. And this then translates into efferent firing through a nonlinear sigmoid curve, again, which has some experimental foundation based on the work of Walter Freeman. So there isn't just a linear relationship between the postsynaptic potential and the firing rate, rather this goes through a sigmoid curve. And we use these models, therefore, to build up canonical circuits in the brain. So we can incorporate different timescales of synaptic activity. We can make them inhibitory or excitatory, and essentially then examine the repertoire of dynamics of these simple circuits, fit them to data, and see what's going on inside the brain to generate normal and abnormal rhythms. So in what follows, I'm going to use a version of what I've called here the Liley neural mass model, which is a conductance-based neural mass model. So we see here again this second-order equation on the postsynaptic currents. The addition in this model is that the change in membrane potential incorporates channel reversal parameters. But essentially it retains the same general framework of the second-order differential equation. So what does this kind of model mean, or how does it relate to physiology? Well, what it means is that it's a model of neural masses. So it's a model of an abstract interaction between some populations of neurons. And the parameters of these models represent synaptic timescales and gains. How these relate explicitly to neuronal timescales and gains is up for grabs. Particularly the gains are more relative than absolute. We can model the relative density of connections between different neural populations that we model. So again, I would say relative is the key thing here. So if we're comparing, say, case versus control, for example, we might make claims about changes in connectivity between these populations. And there are also other properties of synaptic kinetics here on the neural mass level. So again, I think this link between neural mass and neurons is pretty much up for grabs still. And that being said, it's going to make fitting these models to data or identifying these models very, very difficult, because it's very difficult to put prior expectations on these model parameters, given that they are abstract. Okay. So we want to understand certain rhythms. For example, I've got something with an alpha peak here. The data is in blue, and the model output is in red. So there's a strong alpha peak here in the data, and we can simulate the model at a certain parameter configuration, and find that it hasn't really done a very good job at recreating the alpha rhythm. And we can adjust some of these parameters and find that it in fact can do a very good job at recreating the data. So one of the things that we want to do is to use these models to understand, in principle, under the assumptions of the model, what could be generating these rhythms and how might they be going wrong in epilepsy. In order to do this, we need to find the parameters of the model such that it fits the data. So this is a model inversion or a data fitting problem. If we go back into the dynamics of these models, so from a dynamical systems perspective, what we find is that they're high-dimensional or reasonably high-dimensional, and they're nonlinear models, and they have qualitative changes in dynamics whenever you change the parameters. So there are different kinds of bifurcations present in this model. I've highlighted a couple here, or Dom's highlighted a couple here, I should say. Some bifurcations, so the green lines here are bifurcations, which for the sake of this talk means a qualitative change in the dynamics. So either side of these green lines, the model, if left unperturbed, would decay to a fixed point. If you drive it with noise, it can have a more complicated response. Within the middle of this region here, the model will oscillate autonomously, so it generates a limit cycle within this region. So what we find in this two-parameter plane, so this is a six-dimensional neural mass model, and we've set most of the parameters to quite arbitrarily defined standard values, and then we've changed the excitatory synaptic gain and the excitatory synaptic timescale, and we've color-coded this grid search here, well, this gridding, not much of a search yet, according to whether it accurately produces these alpha rhythm dynamics from, well, these are real recordings from a certain subject. So the data is in the solid black line, and you'll see that is the same in each of these four pictures. The darker the red colour, the better this model fits the data. And what we can see is that there are two islands for which the model does accurately recreate the data. And these are related to the presence of these Hopf bifurcations, so they sit quite close to it, although again the relationship is not so trivial here as it is here. Just to say that this makes parameter fitting quite complicated and means that standard tools may not be applicable. To take this into higher dimensions, so this model would have up to 12 parameters, I think, and different versions of the model have more parameters. This is just a single column. If we're talking about modeling the whole brain or large regions of the brain, we need more columns, very many more parameters. The picture is quite exotic. So this is a set of equivalent pictures, but for different pairs of parameters. And we can see, as expected from a nonlinear dynamics point of view, the organization of these rhythms by different bifurcations and quite or reasonably exotic topologies of regions that best fit. This makes using traditional methods, Bayesian methods for example, or even simple methods that have been used quite often in the neural mass model literature, makes that challenging. So I want to illustrate this here. So here's an example of approximate Bayesian computation on 9 parameters of this model. And what we've done is we've made a Latin hypercube that's quite dense to generate a ground truth of where the model does best fit the data. So what you can see in orange here is a ground truth distribution for each parameter where this model best fits the data. And you can see a discrepancy between, this is a sequential Monte Carlo ABC method, doesn't really recover the underlying or ground truth parameter distribution in this model. So we turn to other global search meta-heuristics instead to try and map the regions of parameter space which can well approximate this data. And we see, for example, for GA here, on the whole, we've done a lot better across many of these parameters, and we've got a slight bias here in parameter little a, which is the time scale of the fast excitatory synapses.
Just to be clear, the ground truth is generated by the model, and you're refitting the model again.
No, this is from data.
So how do you know it's the ground truth?
by exploring quite densely the ground truth from the model point of view. So by exploring quite densely all of the parameter values, all of the combinations of parameters and their output, and seeing does that fit the data well.
How do you know that's ground truth?
So I'm not talking about mechanisms here. I'm just talking about just the dynamics. So the orange or yellow, so the parameter values that make up the yellow bars, they are parameter values for which the model very well fits the data. That's the ground truth of it.
But where the fit here is you're looking at the power spectrum.
Exactly, yeah.
So that's the picture that you're putting.
Exactly, yeah.
But you might have degeneracy. You might have multiple.
We absolutely do, and the simple.
The C and the D.
Yeah. So our goal is to find all of the parameter combinations that sufficiently fit the data, and we find that essentially the ABC approach does not allow us to do this. It biases itself to certain regions. So for example, in this parameter here, the yellow histogram shows us that there are very many parameters, very many higher values of A for which the model can reproduce that data that are not picked up by the ABC method.
I wouldn't call it ground truth. I'm objecting to this. I get what you're trying to do, but
Okay, we'll find another way to phrase it.
Okay.
We investigated a little bit the reasons for this, and we generated this artificial, well, based on what we'd seen in the fitness landscapes that I showed you before. We generated this artificial test case. So this function hx is a mixture of sine waves with different frequencies, and we generate this plateau here. And in this sequential ABC approach, you basically sample different cost functions. So we start off with a very broad sampling, and as we reduce the tolerance, we see that more and more samples are focused around this region because of the plateau than are focused around here. And we end up with an overestimation of the importance of this region of parameter space. So there's quite a complicated interplay between bifurcations in the model, fitness landscapes, and posterior probabilities actually. It's going to be quite challenging to overcome. But we find that the genetic algorithm does a good job. I'm guessing I've got 5-ish minutes left to explain an example of what we've done here. So here's some data from sleep in children with and without epilepsy. So we've got this control versus patient setup. 14 children with epilepsy, 16 without. And we see subtle differences in the spectrum during slow wave sleep. We can reproduce this in the model quite nicely. And the question is, for what parameter settings do these different dynamics occur? I'll skip over this, which defines the objectives, just to say that we use a bi-objective approach where we fit on the power spectrum, but we also fit on the horizontal visibility graph of the signal. And this allows us to pick up or fit to or recreate more nuanced features of the data. For example, we can filter out sawtooth-like signals where first of all, we can filter out quite nicely signals that generate the power spectrum, but not the more nuanced properties of the data. So here's the data. Here's a version of a fit which fits the power spectrum, but not the HVG. When we get into our chosen method, we're picking up or filtering out a spikiness or a sawtoothness out of the data, which is quite subtle. I guess just another note, the use of the HVG allows us to improve the identifiability of the model fitting approach. So again, here's one of the parameters of the model that we fit. If we fit on the power spectrum alone, it suggests to us that all of this normalized range of gamma E is feasible for generating the dynamics, but when we incorporate the HVG, we can filter out a lot of these high values and focusing on low values. So it's quite important, I think, to go beyond the power spectrum in these kinds of approaches. So what do we find when we fit this model to the data? Well, we find But as we saw, there are differences in power spectrum in patients versus controls, and that maps onto differences in parameters that are actually quite specific. So we see, for example, that controls have a higher firing rate on excitatory and inhibitory neurons than the controls. So this suggests that the brain tissue, under the assumptions of the model, is hyperexcitable, but in both populations, both excitatory and inhibitory neurons. And we see that this is actually driven, this effect is driven by patients that actually had seizures during their admittance. We can try and map this down to the synaptic activity or the certain synapses that are in the model at the mass scale. And for example, we see that the mean excitatory synaptic current on excitatory neurons is higher in patients. This effect is not seen in the inhibitory population. So there's an increase in excitatory synaptic activity on the excitatory population, but not the inhibitory population. So you get the idea here that we're trying to go from data, which is a macro scale rhythm, into some understanding of the mechanisms that might be driving this rhythm under the assumptions of the model, of course. So that can explain the background rhythm, so the change between epilepsy and control in the sleep rhythm. But how does this relate, if at all, to the generation of seizures? So it is quite interesting that somebody with epilepsy would have an alteration to their slow wave sleep dynamics. But how can we understand, what tools can we use to understand why this would link to a propensity to generate seizures? And I would suggest that the model or models like this are quite a good way to do that. How we can do this is we fit the model to the background dynamics. We can also fit the model to some prototypic seizure dynamics, and here we have some data from spike wave seizure, for example. And what we find is that in parameter space, in terms of the excitatory synaptic current on the excitatory neurons, we find that controls are further away in parameter space to the seizures than the patients. So if we're repositioning, or if we're mapping the EEG dynamics into a parameter space of a neural mass model, we do find, in fact, that the patients sit in this more vulnerable region of parameter space than do the controls. And again, it's driven by patients who actually had seizures during their admittance. So there are very many potential applications of this. So working with another neurologist partner at St George's University Hospital, that's Sam Chan, we've actually developed a pilot study where we're going to use the model to try and predict the effect of changing medication. So in Sam's clinic, she's going to get people who are due, or children who are due a medication change. We're going to take the EEG before and after, and driven by the certain drug that they are given, we're going to put the mechanisms of that drug into the model and see if we could predict a normalization of their brain dynamics and a movement away from seizures in this parameter space of the model. So this is quite exciting. That's ongoing. We just got the ethics for this study. I think I'm probably a little bit over. We've got various other projects going on with an exciting cohort of people, but for now, I'll just thank all of the people that contributed to this and future work, and happy to take any questions. So thank you very much. I think Gerwin was first.
Yeah, this is really a very interesting work, and I think potentially quite important. When I sort of think of epilepsy, I'm sort of trying to figure out what is it that we can possibly do, and what is it that's hopeless. And it seems to me that this whole epilepsy detection and prediction, which obviously people have been doing for like 35 years or something, that to me seems reasonably hopeless. I mean, there's like so many, or epilepsy, just like cancer, is like so heterogeneous. Mm-hmm. And you have like, you know, MRI positive ones, mm-hmm. you know, like cortical dysplasias or white matter, you know, malformations or something. They're MRI positive, and then you have other ones that are MRI negative, and they can be in different areas of the brain or something. Yeah. and or you can have epilepsy secondary to multifocal encephalitis or something. I mean,
Very
like
heterogeneous.
It's the whole brain is sort of a little screwed up, and so if I would put my money somewhere, it would seem to me that trying to predict treatment response is something that's quite promising. But I'm not sure. I mean, epilepsy in general I think is quite difficult. So what do you think? Where are the areas where we have a chance of actually really making a difference?
I think, yeah, you've outlined some of the difficulties there. There are also some things that do play into our favour, like, for example, some of the obvious changes in dynamics and the apparently low dimensional dynamics that we might have a hope of trying to understand at a large scale. In terms of seizure prediction, it's a long and winding road, which is the title of a couple of papers on this. Advances in wearable tech, I think, has given a lot of insight into this. So there have been a couple of cohorts of around 10 people who have worn implantable devices for order of years. And we, from that, have new insight into seasonality or different rhythms in seizures.
You mean the neuropace?
There's the neuropace. We're working with some data from subcutaneous implants as well now. So again, less invasive. So I think those new insights are give us more hope, because we might be able to identify times of year, times of month within which a person is likely to experience many seizures. And again, if we're talking about long-term wearables, even that might let us around the heterogeneity, because we can learn person-specific models from a certain lead time of that wearable tech that then go into longer-term prediction. So I think that's good. Predicting pharmacological treatment response is an interesting avenue of research, particularly for the models. We've done some preliminary work on some data where people without epilepsy were given anti-epileptic drugs, and we can see the effect on the EEG signals of those drugs. What we find is that the responses are extremely heterogeneous. So that might actually be a big challenge. The fact that these drugs are not necessarily clean or easily dosable, and I think you find that in the response or non-response of people who are given these drugs to combat their seizures. So I see hope in all of these aspects actually. Seizure prediction, drug prediction, and surgery prediction, I think is a really interesting one. Hopefully working closely with the neurosurgery teams can help us make headway there.
Yeah, Danny Bassett at UPenn was doing this virtual
virtual resection,
virtual resection thing.
Yeah.
I thought that was quite interesting. I'm not sure that she ever went anywhere with this, but I thought that was quite interesting. But of course, that's only applicable to like ECOG implants or something. I mean,
we did some work on scalp EEG with this. So obviously the spatial scale of prediction is larger. So we had some evidence that we could predict, say, hemispheric locality with scalp EEG, and we're working now on integrating scalp EEG with ECOG or SEEG, try and improve these network models.
Can I just follow up on that? I really like the idea of using response to treatment as a way to measure the accuracy of these, novel methods for diagnosis. Because, you've mentioned the difficulty in translation and adoption. And my feeling on that is that there's a whole discipline that we're missing here, which is translation and adoption. There are people who don't do that as a job. And I think we are missing those people at these meetings. The way we design the studies, the way we carry out these things are all based on a series of assumptions we have as scientists and neuroscientists or mathematicians, without actually taking into account that the path to translation and adoption is a mess. Like, I don't know anything about it. We just assume that at some point, if the data are accurate enough, if the study is good enough and generalizable enough, it will be adopted. and
Yeah.
it's not like that, in the sense that the regulators have got their own rules somehow. And many times we don't know these rules. So we develop the studies in a way that don't make it to translation because of that. And if there's something that this scoping meeting could be doing, I think, is to try and maybe discuss that. How do we bring into the discussion from the design stage the experts in translation and adoption to help us down the line? Otherwise, we just multiply papers and these things never see the sunlight.
Yeah. I think Gerwin's probably going to address some of these points tomorrow as well.
Just obviously the funding landscape doesn't really help us there, right? Because, the drive from an academic perspective is to get the next good paper out. It's not to translate it into that piece of work most of the funding.
Yeah.
But that's terrible.
I know.
That's horrible because it becomes a futile intellectual exercise.
I know.
There are some schemes and there are some incentives. So the EPSRC is doing something with this in terms of its knowledge exchange, its healthcare technologies funding. I recently had one of these awards with Ravi, and we do at least have time within that funding to embed ourselves in each other's world and try and get to grips with how we do translate findings from models. So yeah, I think the general setup isn't to promote this. There are some little needles in the haystack that can help.
And did this, NIHR is obviously the funder that is the main translational and applied one. But by and large, most NIHR grants need to have a clinical person as their PI. So this is where it's really important to have and find those collaborations and working with the likes of myself to actually find where to go.
But for example, with NIHR, so I'm part of the Biomedical Research Centre, which is obviously funded by the NIHR, but NIHR won't fund any academic time. Permanent academic. Now, you can take on some of that as a permanent academic, but there's only a limited, Wellcome is similar, there's only a limited number of things that you can afford to do.
Yeah.
Because you've only, if your time isn't being funded.
It's a big problem from financial statement point of view.
So
Universities have to cover these costs from somewhere else. There are no money in the system.
You rely on goodwill from the university, and the
A
department.
goodwill, what if there are no money in the bank?
Yeah.
But which is a weird philosophy, right? Because effectively, if you're doing a study for developing a diagnostic method, and you make a wonderful series of papers on that, but then there is no diagnostic method, even though it works, right? Even though it should be working, it should be adopted.
So
that is a waste of money, isn't it?
I agree.
So I kind of beg to differ on that. So let's just say, I'm fully employed by the University of Exeter, but I hold an honorary clinical contract. NIHR are paying 30% of my salary, and it's through contracting for one of the grants that I'm on.
Okay, I'll be interested to know how that.
NIHR have different models. For some studies they pay, for like the BRC they don't. So it depends. The BRC is an infrastructure.
And the BRC, so Exeter's BRC, for example, they have funded both academics and clinicians, but those are through kind of different mid-career fellowships, which is administrated through the BRC. So that's a discussion with your BRC rather than NIHR to say how can we support pure academics and not